In this video we're going to talk about the stability of different airfoils designed for tailless airplanes and flying wings airplanes. We're going to choose the optimal position of the center of gravity and look at the position of the aerodynamic center and the center of pressure points. And then we choose the position for the center of gravity of this airplane. We also look at different types of airfoils. Actually, we have the list of almost 40 different airfoils, and we're going to choose the best airfoils which are stable. So let's say you can choose any airfoil from this list, and then you can look at this airfoil and see how the performance of this airfoil is, if the airfoil is stable or unstable. And then if the airfoil is stable, actually we mark it with the circle, and unstable with the cross. And then we're going to choose the best airfoils from this set of airfoils. All those airfoils were found on the internet and designed for the tailless airplanes and flying wings. Okay, so let's do it. Let's build the simplest airplane, and we start with the wing, presented here with the airfoil. And we know that this airfoil has three properties. For instance, the lift acting upwards, and the positive property, and also it has the drag, the side effect of the lift opposing the movement of this plane, the negative property. So we know already all about the lift and drag from the previous video, so now let's talk about the stability of this wing. Let's talk about the moment. And the moment is presented here with this axis. So here is the moment coordinates. So here is the position where the moment is equal to 0. And the moment can be computed at any point in this 3D space. And if you know the moment in one position, we can compute the moment in any other position using the property of the moment function. Because this function is additive, we can sum those moments, so we can derive equation to compute the moment in any other position. Now let's look at the property of airfoils with respect to the moment. So, and those properties are actually, the main property is center of pressure, is the point where moment is equal to 0, and the second point is where the moment is constant with respect to the angle of attack. So if you change the angle of attack, the moment is not going to change, it stays constant. And we also have the third point, the center of gravity. So this point is very important for the airplane design, to make sure that we have the stable configuration. Okay, so how those points are placed on the wing. So usually the center of pressure is placed close to the quarter of the chord line. So it can be placed ahead of the quarter of the chord, maybe behind, maybe exactly the position where we have the quarter of the chord. But let's place it here in this position for now. Okay, so second point is aerodynamic center. So this point usually is, well, not usual, but as well can be placed or has to be placed at any position somewhere nearby. It can be in front of the center of pressure, it can be exactly the point where the center of pressure is, or can be behind the center of pressure. So let's put it here for now. Actually, to be more precise, we have to shift this aerodynamic center point from the line where moment is 0, because usually the moment is not 0 at the point of aerodynamic center. We have some non-zero value, but this value of moment stays constant, so we can change angle of attack, but the moment is not going to be different, the same value. Okay. So the position of those 2 points is defined by the properties of airfoil. So different airfoils are going to have different position of the center of pressure and the aerodynamic center points. And also, if you change angle of attack, we're going to have different position for those points as well. So the center of pressure is going to shift a bit from left to right. The position is going to be defined by the angle of attack. The same is true for aerodynamic center. Well, it stays constant for the small change of alpha, but if the change in angle of attack is significant, we're going to have a different position for this point as well. Okay, and now the major question is where to put the center of gravity. So if we assume that the plane is flyable, it's meaning that in the static situation we're going to have zero forces and moments acting on the center of gravity of this plane. So the moment has to be zero. And it's very easy to place the center of gravity exactly where the center of pressure is. So to put it here. So in that case, we're going to have zero moment acting on the plane. But you may argue that center of pressure actually is shifting a bit with the alpha, with the angle of attack. So the answer to that is you have to choose the place where you're going to operate most of your time, and then choose this angle of attack, find the center of pressure corresponding to this angle of attack, and place center of gravity exactly at this point. Okay, so this is a simple design. And now let's look at the stability of this system. We present the airfoil with this balancing system. So we can see that we have the center of gravity, and this airfoil on this particular system can rotate about this center of gravity, and we have the center of pressure located here. So what we can do now, we can compute the moment at each position along this line for different angles of attack. So if we do that, we're going to have this result. For instance, result is going to be like this. So we have two angles of attack, alpha is equal to 1 degree and alpha equals to 5 degrees. So alpha equals to 5 degrees has a steeper angle, because for the higher alphas we have higher lift force. As a result, we have the higher momentum. So we have two moment curves, and we have the center of pressure. And now center of pressure meaning that this section to the center of pressure, the nose section, has the same moment as this section, the tail section. So the moment from the tail section, the blue arrow, is the same as the moment from the nose section. And now we are ready to look at the stability of this system. So let's assume we have a small perturbation in the atmosphere which leads to the increase of angle of attack. So alpha goes a bit up. So in that case, if we have high angle of attack, the center of pressure is moving from small alphas to high alphas. So it moves close to the high alpha. Okay, so we have the center of pressure here. So once again, that means that this section to the center of pressure has the same moment as the section behind the center of pressure. But the center of gravity stays behind, or in front of the center of pressure. And if you look at this position of the center of gravity, we have a bit less of a nose, but more of a tail. So the system is unstable because we have extra section which is going to be acting about this axis. So in that case, the tail is going to be acting in the opposite direction, trying to restore the original angle of attack. So it goes back, and the center of pressure moving back to the original state. So the same thing is going to happen if we have a sudden decrease of angle of attack. So let's say the airfoil moves to the opposite direction, like this. The center of pressure moves close to the nose. And now look, the center of gravity is behind the center of pressure. So in that case, we're going to have the opposite effect, and the airfoil is going to move in opposite direction. And boom, we have the equilibrium. So we can summarize and say that if the aerodynamic center is behind the center of gravity, the system is going to be stable. Now, let's look at the different location of the aerodynamic center. So let's say we have this distribution of moments. So in that case, we have the opposite actual effect. So once again, if we have some pitch up perturbation, in that case, once again, the center of pressure is moving because we have high alpha, so the center of pressure moving to the high alphas. So it moves in opposite direction. But in that case, what we're going to have, we're going to have actually, for this section, we're going to have more nose, because the nose is going to be like this section to the center of pressure, and then that section, because it rotates about the center of gravity. And that means actually that you're going to have the opposite effect, and the nose is going to be even higher. So we have even higher pitch up momentum, and the center of pressure moving even closer to the higher alphas. And as a result, we have the runaway condition, and this plane is not going to be stable. So we're going to have this situation eventually. But yes, and the same actually applies for the opposite direction. So let's say if we have a sudden pitch down moment or position of airfoil, so the center of pressure moves to that position, closer to the lower angles of attack, and as a result, so in that case we have this section for the tail and this section for the nose. And as you can see, we have a bit more tail, because the tail actually goes to the center of gravity, to the center of equilibrium. And because we have more tail, so we have stronger moment acting on this tail, so we're going to have this situation, and which moves the center of pressure even closer, even closer to the lower angle of attack, and so on. So and then eventually it's going to follow to the negative angles of attack. The plane again is going to be in the runaway situation. So it's going to right to the ground. So it's not a good situation when you have the aerodynamic center in front of the center of gravity. So this is unstable airfoil, not stable airfoil, and in that case you would have to use a tail to balance this system. So you cannot just use one wing, you have to add a tail to this configuration. So our choice, of course, is this position of the aerodynamic center behind the center of gravity, and as a result behind the center of pressure, because the center of pressure is exactly where the center of gravity is. Now let's make it even more explicit. So let's go here. So now we see that airfoils can be divided in two types. So aerodynamic center is behind of the center of pressure and is in front of the center of pressure. The center of pressure is moving from the small angles of attack to high angles of attack. It moves from the nose to the tail, or the opposite, from the tail to the nose. So once again, the useful airfoil is actual airfoil where we have the center of pressure moving to the tail. So when we increase the angle of attack, the center of pressure moves to the tail. In that case, the airfoil is stable, and we don't need to add any extra surfaces like tails and so on. So this is the first airfoil that you can use for the flying wings, and the second type is when the opposite happens. So if the airfoil is located here, so this is not useful airfoil for our purposes. So when we move the center of pressure from the small angle of attack to high angle of attack, the center of pressure moves to the nose. And yes, and note that the center of gravity stays the same all this time. So, and because of this, there's a different momentum acting on this airfoil. And in one case, like in this case, we have the negative effect, so the airfoil becomes unstable. And in this case, when the center of pressure moves to the tail, we have the stable configuration. Now let's talk about some common misconceptions in this subject. So let's assume we are a zero-dimensional creature living on the quarter chord point. So we live here, and what we get the moment number from different software, say XFoil or maybe from somewhere else. And by looking at this number, so it may be positive, negative, or zero number, we make a judgment about this airfoil. So we can say this airfoil is not good for the flying wing and so on. But in the reality, actually the absolute value of momentum is completely irrelevant. So if we're going to move from the zero-dimensional creature to one-dimensional creature, living on this line, on the chord line, we can compute the moment at each point, and then we're going to have those beautiful lines. So in this case, our moment line is crossing this point where we have the moment value, and this actual point, or this value of moment, defines or maybe give you a hint on where the center of pressure is located. And we see that for this particular curve and for this position of moment value, we're going to have center of pressure pressure located here, close to the tail. So now if the value of moment is a bit smaller, let's say we have 0 moment, then in that case this curve is moving to the point as well, and then you have the center of pressure located exactly at the quarter chord point. If you have a negative moment, like this, then the center of pressure moves close to the nose. Thus, we can say that the absolute value of moment is completely irrelevant, does not influence anything. What is important, however, is how this moment value behaves with increase of angle of attack. So if angle of attack is increasing, so from 1 degree to 5 degrees, the center of pressure moves to the tail, like this, and the moment is actually increasing. So if the moment is increasing with increase of angle of attack, this is good, because the airfoil is stable and the aerodynamical center is located behind the center of pressure. And as we have seen previously, you can put the center of gravity somewhere here in this range, depending on the angle of attack at which you operate. Okay, so now what happens if, for instance, we have the opposite situation when the aerodynamical center is located in front of the center of pressure. So in that case, the center of pressure moves close to the nose. And this is not good, as we have seen previously, because the airfoil becomes unstable. And the moment actually is decreasing, so it goes from this position at alpha equal to 1 degree to down to this position, alpha equal to 5 degrees. So we remove those things. And the conclusion is the absolute value of moment is completely irrelevant, but what is important is how this position or how this value of moment is changing with increase of angle of attack. If angle of attack is increasing, the moment has to increase as well. In that case, we have stable airfoil with the aerodynamical center behind the center of pressure. However, if the moment is decreasing with increase of alpha, then we have unstable airfoil and the aerodynamical center is located in front of the center of pressure. Very simple. And now let's look at the results from the real airfoil. But first, you have to derive equation to compute the moment at any given point if the moment is given to you at a particular position, say quarter of the chord line. So it's very simple, you just use basic algebra. So you have two radius vector, one goes to your point of interest, second vector goes to the given point, then you subtract and you get the results. So this is the equation that you're going to use, and having this equation you can plot the results right away. So we go here, and here's two airfoils. The first airfoil is the Flying Wing airfoil, PW51, and this airfoil is beautiful. So if you look at this area, if you zoom in, you will see that points of center of pressure are exactly in front of the point of aerodynamic center, depicted with stars. So we have the stable airfoil, and this airfoil is going to fly if you put the center of gravity somewhere here. Like if you place the center of gravity somewhere in the range of the center of pressure, this airfoil is going to be stable. And please note the distance between the aerodynamic center and the center of pressure. So the shorter the distance, the more maneuverable plane is, and the longer the distance, the more stable the plane is. But having two stable planes is probably not a good idea too, because you would like to have control of your plane by slight deflection of your control surfaces. So this is good for the design of airplane. This airfoil is good to design an airplane which consists from single wing. If you look at more standard airfoil, NACA 0012, so in that case we have a different picture. So if you look here, then we have actual center of pressure points kind of mixed with the aerodynamic center points. And at small angles of attack, this airfoil is stable, because aerodynamical center is behind of the center of pressure. But if you go to the high angles of attack, then boom, you have aerodynamic center in front of the center of pressure. So my prediction is that this airfoil is not stable at high angles of attack. So for this airplane, for the airplane with this airfoil, it's a good idea to use a tail. A tail solution is the solution of one-dimensional person who lives on this chord line. So he has to place his center of gravity on this line because he haven't seen any other lines in his life. But let's be better than that and move to two-dimensional space, so that we can place our center of gravity anywhere, above the airfoil or below the airfoil. And we can do it using the same equation. So we have the radius vector, but for this radius vector we plug kind of the total value. So we have x and y position of the point. In this case we're going to cover all the space. And the results are shown here. Here's the NACA airfoil. And on this graph we have y-axis instead of moment axis. So now we have the space along the y position. So you can choose any point above or below this airfoil and you can compute the moment points. So on this graph presented two types of lines. One type of lines is solid line corresponding to the center of pressure, and the second is the dashed line corresponding to the aerodynamic center. So let's go down and let's change the scale. Like in this case we have 0.3 units of chord on the y-axis, and let's move to this graph where we have 20 chord lines on the y-axis. And look at this airfoil. It's thin because the scale is significantly higher than the thickness of this airfoil. So now we have, if you look down, you have beautiful solid lines corresponding to the center of pressure, and only after you have the dashed line corresponding to aerodynamic center, meaning that you have aerodynamic center behind of the points of center of pressure, and that makes this airfoil stable. And if you go up, you will see the situation is the opposite. We have dashed line, aerodynamic center, in front of the center of pressure points. So in that case the airfoil is unstable, as we have seen just a moment before. So basically meaning that we can use this NACA airfoil for the flying wing planes, so basically just one single wing, if we're going to place the center of gravity below this airfoil and a bit in front of this airfoil. And why is that? Well, think about the moment, not the moment, but the lift force acting upwards, significantly bigger than the drag force acting in that direction. So you have to find a line such that you're going to have projection on this line equal, and then you place a normal line to that one. And then you will see, like for instance, this line is the line where the moment is equal to 0 for the angle of attack equal to 1 degree. Here is the 0 moment for the alpha equal to 2 degrees, and so on. And to be more concrete, let's look at this airplane. So the airplane uses standard NACA airfoil, and because of this it's not very stable. So we have to add tail to this airplane and maybe place the center of gravity a bit in front of the wing, so that you're going to have the balance system, this force acting upwards and force acting downwards, and then you can balance this plane. But this system is not very beautiful because it has some unnecessary parts, like for instance the tail. So let's make it better by removing this piece. Now it's beautiful, but it's not stable, because as we know that if you live on the chord line, you cannot place the center of gravity anywhere to make it stable. So the only solution is to place it down there below. And the position of this center of gravity can be defined if you look at the forces acting on this wing. So the lift force and drag force, and then the normal line at which you have equal projection of those forces, and then the line at which you have 0 moment. So you place center of gravity somewhere on this line. Where to place your center of gravity actually depends on the position of aerodynamical focus of this wing. And we have seen that actually somewhat down below, approximately maybe 10-20 chord lines down below, you have the position where actually the aerodynamic center is behind the center of pressure. So this plane is going to be stable and beautiful. But maybe let us be a bit less exotic and just choose airfoil specifically designed for this purpose, like PW51, beautiful airfoil with aerodynamic center placed behind the center of pressure points. So this should be stable airfoil, and actually there are few similar airfoils for the flying wings, so maybe let's pick the best one from the available airfoils for this purpose. But first let us find the position of the center of pressure point and the aerodynamic center point as the function of angle of attack alpha. So you're going to see that this point is going to be taking different position with respect to the alpha. And this graph is already done, so I have this beautiful graph. So the center of pressure point is displayed with the red color, and the aerodynamic center is displayed with the blue color. So this position of this point is actually moving on this airfoil. So if you look at the chord line, it's going to move from 0 to 0.25 probably. But a few remarks we should do about this. The first remark is that aerodynamic center is actually quite a bit has quite a bit of noise. So it happens because the way it's computed. So when the center of pressure is not changing significantly, we have unpredictable results. But from this graph, we see that the aerodynamic center is on average behind the center of pressure point for this particular airfoil, PW51. So this is good, and actually the aerodynamic center is not important for us. All we need is to know that center of pressure point is moving from the nose, from the zero to the tail. And if this happens, then we know that this airfoil is stable. And in this particular case, PW51, we know that we do have this behavior in most of the cases. So it's moving from the nose to the tail, except maybe this region, when we have the opposite effect happening. So in this range, approximately from 1 to 1.5 degrees, we're going to have unstable behavior for this particular airfoil at this value of Reynolds number. But if you think about this, you might have some instability in this range, but then eventually you're going to have the pitch up moment, which will lead you to higher alphas. But then, because the curve again is taking this shape from the nose to the tail, then it's going to be stable. So it's going to be stable at maybe 2.5 degrees of angle of attack. So all is good for this airfoil except maybe this range. But I think I will talk about this later, how to fix this problem. And now let's compare different airfoils. So how to do it? We look at this curve. So we want to make sure that for the most of the alphas we have this behavior, so that the center of pressure point moving from the nose to the tail. So we map this curve to a number, and then we're going to compare those numbers to determine the stable airfoils. So we go to the previous code we have written. In my previous video I have talked about this a bit, and what this code does, we basically scan different types of airfoils. So here is the list of tailless airfoils or flying wing airfoils, and we're going to plot the polar curves. So the first requirement is to have the maximum lift, a small Reynolds number, so that we're going to have the smallest possible speed for this airfoil, the small stall speed. And the second requirement is to have the efficient operation at the high speed. So we're going to look at the curves for the high Reynolds number, and we're going to choose the ones with the small drag coefficient. So drag coefficient has to be minimal, and the lift coefficient has to be maximum for the low Reynolds number. So we have done this before, and then we got this feature space plot. So on y-axis we have the maximum lift coefficient for the low Reynolds number, and on the x-axis we have the minimum drag coefficient for the high Reynolds number. And we have plotted all the airfoils that we have. So, but now we have extra feature. So now we can see if the airfoil is stable or not stable. So this part was missing in the previous video. So the stability of the airfoil, we have talked about this just a moment before. And if the airfoil is unstable, we mark it with the cross. If it's stable, it's circle. And just to repeat that, what we need to look at this section. So we need airfoils with high lift coefficient at small Reynolds number and small drag at high Reynolds number. So this is the range of interest, and it's good to observe that most of the airfoils actually are getting to this section. So people like picking those airfoils, I think, not blind, but they use some ideas how to make sure that the airfoil is good. So we look here, and those are actually the airfoils of our interest. So this is the list of airfoils which are good, and maybe you have to exclude from those airfoils the one with the crosses, because those are unstable airfoils. So if you have circle, this is stable, good airfoil we can use. And now maybe let's look at the particular airfoil in more details. So we go down here, and here is the graph. So in this case we have PW51 airfoil. So airfoil is good because it has small drag coefficient and has significant lift, sufficient lift. So the airfoil is good, but now if you look at the curves for this airfoil, you will see this picture. So this is the position of the center of pressure point with respect to the alpha. So we know that this center of pressure is moving to the tail in most of the cases. So we have small strange behavior at small alphas from 0 to 1.5 degrees, but that's okay because at small speed, oh yes, so this is the small Reynolds number graph, and this is the high Reynolds number graph. So if you look at this curve, so you at small Reynolds number you actually flying slowly, so you have high angle of attack. So the behavior in this range is not important. And what you have nice behavior starting from 1.5 degrees to maybe 8 degrees. So the central pressure moves to the tail, and the airfoil is stable at this particular Reynolds number. And then if you look at the higher Reynolds number, 550 K, then you will see that in that case you have the opposite effect. For the higher Reynolds number we have, and small angles of attack, we have the opposite behavior, and this is not good. So meaning that this airfoil is not going to be stable at high Reynolds number. So we have to maybe choose a different airfoil, or maybe not to fly so fast, maybe stay below the 550 K Reynolds number. Okay, but speaking about the stable airfoils, actually what we have only 4 stable airfoils. So those airfoils are perfectly stable in all the ranges from application. What let's see, for instance, on this airfoil, CL54. So we go here. So here is the CL54. Yes, the lift coefficient is not great, and we have significant drag for this airfoil, significantly higher than for the PW51. But if you look at those curves, it's perfectly stable. So we have movement of the central pressure from the nose to the tail, and here as well for the high Reynolds number. So it's all going to be stable in the whole operational range. We might have some small ranges of instability, but that's perfectly fine, I think. So this airfoil is stable. Let's look at a different one. This one. And here is the airfoil, GWL065. So this airfoil is again perfectly stable, beautiful curves. Central pressure is moving from the nose to the tail, so this is good for the flying wings application. And also we have significant lift for this airfoil. Maybe the drag coefficient is not as great, but at least the airfoil is stable. So to summarize, those airfoils are perfectly stable, so those are the best ones. But then we have some airfoils which are not as stable, for instance, like from the no one PW51 or MH60 airfoil. So here's the airfoil, and we have not very nice behavior at high Reynolds number. So we have the movement of the central pressure from the tail to the nose, so which makes this airfoil unstable at the high speeds and small angles of attack. But also we have totally unstable airfoils, like for instance HS series. Let's look at this one. So here's the airfoil as HS130. It looks as if it is good airfoil and small drag coefficient, high lift coefficient, but it's unstable airfoil. So here's the low Reynolds number. We have instability before 2 degrees. Then it's actually perfectly stable till 8 degrees, and unstable at the high speeds. So maybe if you use this airfoil for the low speed operation, it's going to be fine, but has some issues. Okay, so now we have this graph, and we have all the airfoils plotted on the same picture, on the same figure, and you can choose the stable ones. On this graph we also have the quality factor displayed. So the quality factor is for the low speed and for the low Reynolds number and the high Reynolds number. So you can see how stable this airfoil is. So the higher this quality factor is, the better is the airfoil. And there is one more thing. As we have talked previously, we can be a zero-dimensional creature and look at the moment value at the quarter of the chord position. So here is the graph for the moment. And we have mentioned that the moment has to increase. So if the moment increase, we do have stable airfoil. And now you can look here. So here is the moment graph, and here is the value of the moment coefficient. In this case, this moment coefficient is negative, but it's increasing in this range. And here is the alpha, and you can note that this increase in moment actually corresponds to this place on this curve. So we do have the position of the center of pressure moving from the nose to the tail if the moment is increasing. The same is here. The moment is decreasing in this range, so the point moves from the tail to the nose, airfoil is unstable, and now it's increasing. So the foil is stable. So we can use this rule, but actually I found that this is not always the case. So to be 100% sure, you have to move to the one-dimensional space and to compute the center of pressure position at the chord at each point. So in that case you're going to be more confident, because sometimes this kind of simple rule is not always works. And now please note that this airfoil is unstable at the high Reynolds number. So what can we do about that? And actually, if you go back to the previous graph, you can see that plenty of those beautiful airfoils that people have claimed to design for the Flying Wings and Tailless airplanes are unstable by its nature. And if we introduce a more strict rules, we're going to have only 4 stable airfoils among all of them. So this is not good, and it would be nice to find a solution for it. The simple solution would be to deflect your flaps. In that case, you might get the stable airfoil, but you're going to have increase in the drag, going to lose the efficiency. So your beautiful airfoil is going to move to the right side, and you're going to have high drag for this particular airfoil. So the second solution is we have to move from the one-dimensional creature living on the chord line to the two-dimensional space, and maybe find a place for our center of gravity somewhere below or maybe above the airfoil. So I have done computation already, and here is the results. So here is the airfoil, and here is the chord line. So we have been working on this chord line and picking the place for the center of gravity on this line. But we're actually free to move anywhere. So we can choose another line which is below the airfoil, or we can go above this airfoil and choose the position of center of gravity there. So lots of options. So I have done the computations. So in this particular case, we have the position of this line. So here is the position of the line on which we are going to look at the center of gravity, and basically the location of the center of pressure point. So if you look at this curve, you will see that for the different lines, so in this case the line is below the airfoil and is located 0.5 chord length, so basically half of the chord. Location is here, and then we can plot the graphs for the position of the center of pressure point. So all those graphs are plotted for different position of this line. So from minus 0.5 chord length to the plus 0.5 chord length, and then you can look at the behavior of the center of pressure with respect to the alphas. So we increase the alpha, and then the center of pressure is moving from the nose to the tail, and this happens for the center of gravity or the center of point line, which is below the airfoil. So for the lines here, in this location, we're going to have the position behavior. We're going to have the same behavior, so the center of pressure moves from the nose to the tail, and then we have the lines above this airfoil. In that case, we're going to have the opposite effect, so the center of pressure is going to move from the tail to the nose. So we have to reject the position for the center of gravity above the airfoil. So we're going to have only those lines left, and the center of pressure is located at a different position on the y-axis. So if we have the red curve, actually we are on the chord line. So in that case, we have this behavior as we have seen previously. So the airfoil becomes unstable in this range because the center of pressure point moves from the tail to the nose. So, but if you're going to go below this line, let's say 0. So let's look at the graph. So the blue curve are actually fine because they don't have this opposite movement of the center of pressure point. So the blue and the light blue lines located at minus 0.38 chord length from the chord line. So basically this line and that line, if you place the center of gravity here, you're going to have stable airfoil, and there is no instability area in this case. So and thus you can improve this airfoil. And the best position for the center of gravity is approximately half of the chord length of the wing. So here is the wing, and we have to place the center of gravity below this wing, approximately at this location. So in that case, the airplane is going to be stable. To summarize, we can use this technique of lowering the center of gravity to make the airfoil stable. And if you go to this graph, so we have tested almost 40 different types of airfoils designed for tailless airplanes and flying wings, and most of them are stable, but some of them, maybe 10-20%, are unstable. So maybe using this technique we can make those airfoils stable as well. But at this moment we can say that being a simple person, we can decide to stay in 0-dimensional or maybe 1-dimensional space, and in that case we actually bounded to choose those 4 absolutely stable airfoils. For instance, CL54, so here is the airfoil. It has significant drag. Drag is not the best one, and the lift coefficient is not the highest one, but this airfoil is stable. Or maybe those airfoils have better performance. But if you are ready to take your chances, you can try actually other airfoils. So the airfoils with the circle. And those airfoils have small issues. For instance, the airfoil might be unstable at some angles of attack, like for instance here. So we have a small range where the center of pressure moves from the tail to the nose, and the airfoil is unstable, but then it's going to be stable when it's going to cross this range. Anyways, we also have unstable airfoils marked with the cross symbol. So those airfoils are unstable, and you should not use those airfoils because those are absolutely unstable airfoils, at least at my Reynolds number of my interest, and you probably can make it fly if you will deflect your flaps. So if you deflect your flaps by default, then you're going to have different type of airfoil and going to be stable in that case. But the side effect of this is that the drag coefficient is going to rise dramatically. So you have to compute the drag coefficient for this new airfoil with the deflected flaps. So looking at this graph, you can see that drag coefficient is small and lift coefficient is high. So you have to deflect your flaps, and then suddenly your drag is going to increase. So the airfoil moves to this range. So you have to run the computation with the flaps deflected and then see how good this airfoil is. But the default configuration is not going to be flyable. The door can fly if you put powerful enough engine, so the same applies to the crossed airfoils.